Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods. Intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Alrighty, hello folks. Just giving people a few more minutes to sign in for the session. We'll get started here in about a minute or so. Just wanted to let the folks that are currently logged in, few notes about the webinar here today. It will be recorded, so definitely feel free to share that recording. You'll get a link at the end of the session with any of your colleagues who you think might find it interesting, or maybe some folks who weren't able to attend today. Also, again, if you have to drop off early, no worries, you will get a link to the recording. However, if you are able to stay for the full duration, we will have a Q&A at the end. So the chat box on the right side, feel free to post any questions in there. As you can see, my colleague Landon today, he's moderating our session. He'll be posting in various links, different resources throughout the session as well. But definitely feel free to reach out with any questions or technical issues. All right, that being said, we're at the start of the hour here, so let's jump into our session. Today, our webinar will be on the Flex Transient Plane Source, or TPS, really kind of going over a method overview. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies, and I'll be kind of guiding us through the session here today. So today's session, again, will be quite high level, kind of looking at the different ways the sensor can be used, a few different case studies, some different examples, and really just going into what type of data can be collected on different material types. So before we jump into the main bulk of the session, I'll just do a little bit of a background on us here at C-Therm, who we are, what we do. So for those who may be new, really we're all about simplifying thermal conductivity testing, really try to improve on these for the materials of tomorrow, whether they're advanced polymer systems, new developments in insulations, high conductivity, low conductivity. Really, we're there to support a broad range of testing requirements. Now, we do this through the advancement of transient-based methods, predominantly on our Trident platform. You can see that pictured here. Trident is one instrument with three methods available for thermal conductivity testing. The little video that played earlier kind of went over some of these in some kind of initial detail. Traditionally, we do a lot of focus on the sensor on the far right there. You can see that's the modified transient plane source, or MTPS. We have a lot of content available on this one, a lot of information. Past webinars go into this one in quite detail. But today we won't be focusing in on the MTPS. Really, we're going to be taking a look at the one on the far left, that yellow flexible sensor, the more traditional transient plane source. Now, overall, each one of these options has different advantages depending on the type of material you're looking to test. There's also some limitations that you need to be aware of as well, and really I'll try to highlight many of those aspects as it relates to the TPS here today. And just to, I guess, finish out the last one, the one I didn't mention there, the one in the middle, that's the transient line source, TLS. Again, it's a really great option for some certain material types, but again, won't be the focus for us here today. But again, quite a few links already being posted in there by my colleague Landon with more information on the Trident system as a whole. So definitely feel free to take a look at any of those sensors that are of interest to you. So, the Trident platform, it was developed as a modular system. And the reason for that, it's somewhat related to this quote here. When all you have is a hammer, everything looks like a nail. Really, this speaks volumes in the sense that one of the key reasons, or one of the main reasons we see poor data or issues with data collection is when you take a really good method, but you apply it on a material or under a set of conditions that is just really not designed for. So again, with the modularity that you get in Trident, it really gives you the ability to pick the best tool for the job at hand. So again, today we're going to go into the TPS in particular, but we do have a method selection guide available. It kind of covers really a broad range of testing options, whether it's the transient methods that we offer on Trident or some other methods that are available in industry as well. This is a really great resource to take a look at if you're interested in really kind of comparing methods, going into the theory a little bit more, something to definitely take a look at. It's a free resource available for download. And I'll just kind of mention here one of our client testimonials. We always like to highlight what the people that we're supporting, how they're liking the instrument, what they're doing. So this one here, kind of making note that they're using the Trident platform to test a broad range of materials, but really making note specifically of the slab utility as a really easy way to test the thermal conductivity of their thin aluminum alloys. And I'll actually be talking about the slab utility a little bit further in our discussion here today, as it is one of the options that is available on the TPS method. So this quote here is from Hardeep Singh, Senior Thermal Engineer at Intel. And then lastly, before we go into the session, I do want to make note that here at C-Therm, we focus on thermal conductivity, but we are partnered with various groups for related material property, specifically for thermal analysis, Rigaku, their DSC, STA, and TMA instruments, really powerful tools from that side of things, so that we are partners with them for North America. We have, of course, different information available on these systems. Won't be a focus here today, but just wanted to make a note of those. As well as Metrovib. We're also partnered with Metrovib for their DMA platform. Again, related under, call it the branch of thermal mechanical property analysis. Really great company there. If you were interested in DMA characterization, again, definitely feel free to check out some of the links that are posted. But that brings us to the core of our session here today. So we'll go into the TPS method. I'm going to give a little bit of a high level overview here just to start. So some things I always like to make note of with this sensor, it's a double-sided design that will have some bearing on the setup and kind of the sample requirements that we take a look at. Thermal conductivity and thermal diffusivity are the two properties that are really reported from the sensor measurement. Also available in different sensor sizes, so it really gives you some flexibility on the type of kind of the setup, but also the size of the material that you're working with. And really today, we'll also go into some of the advanced utility options. This is really one of the unique aspects of this sensor. It can be operated with different utilities or different modes as it relates to different sample types. Also high temperature capabilities we'll touch on. And as well, another big aspect of this method is that it conforms to the ISO standard, so ISO 22007-2, specifically for groups that may be working with polymers, different conductive materials. This is a standard that you may have seen referenced before, so our TPS does, of course, conform to that ISO standard. So going next into some principles of operation, this will be quite high level, but just to give you an idea of how the sensor works. So as you can see on the image on the top left there, the sensor is placed in between two test materials. Again, it's a double-sided sensor, so because of that aspect of the sensor's design, we do need to cover both the top and bottom side, basically creating this stack around the sensor. Now, these do need to also be identical samples, so you can't place a metal and a polymer, or even two different metals on top and bottom. They do need to be viewed as identical. That's some verbiage that's taken directly from the ISO standard there. But once you get your sample set up, really the next part of your test is going to be defining the time and power parameters. So with the TPS method, it is one that does put a little bit of onus on you as the user to set up your measurement. So not only setting up the sample, but the testing parameters within the software as well. Now, once you've landed on a desired test parameter set, you initiate your measurement. And at the end of the day, really with any of these transient techniques, we're collecting that delta T, that change in temperature that occurs as a function of time. That's really what the software is going to collect and what we'll be analyzing in order to determine the thermal properties of the material. So another aspect with the TPS is that once you've collected your data, there's also going to be a post-measurement verification process. Basically, you need to take the data that you've collected, and within the software, you'll go through some steps in order to analyze the data. This method does have a user component that really requires you to go in and go through some steps here. There's certain checks that need to be run, different adjustments to validate the data. But again, this is all laid out quite extensively in the ISO. And of course, if you were interested in this and it's something that you end up acquiring, the training that we provide goes into full detail on the test protocol and how that's all done. So again, just a little bit of a high level idea there. Basically, you set up your sample, collect your data, go through the analysis, and that's kind of the main idea there. Now, irregardless of the testing process, I do want to flag that there will be different modes, as I kind of touched on earlier. We call them different utilities. Each one of them does have some variation with respect to some of the requirements for the setup and some considerations on the analysis as well. But just going through these, when we talk about your really entry-level basic testing, that's TPS bulk, or TPS, the bulk utility. It's really geared towards materials that are isotropic in nature. So, for example, if you had something that had a different in-plane and through-plane thermal conductivity, something that was anisotropic, and you tested it with the bulk mode, you would likely get some errors in your measurement. So you do have to have some, some understanding of the type of material you're testing going into it, because it will infer the mode of operation that you utilize. But assuming it's an isotropic sample, bulk, really a great option here. One of the things I'll just flag is that the size of your sample for the test is dictated based on the sensor size that you operate with. So you can see we do have a few different sensor size options available, kind of 6 up to 30 millimeters in diameter. And your resulting or the corresponding sample requirements are based off that. So your sample's diameter needs to be at least 2.5 times the diameter of the sensor that is chosen, with a thickness equaling at least that of the diameter. And again, because it's a double-sided system, double-sided setup, you'll need 2 samples produced for that test. Oh, skip ahead there. There we go. So just going to do a little case highlight here. This was some characterization of a potting compound with a group that we've done some work with in the past, CoolMag. This data was presented in previous webinars, but just wanted to highlight it here today as a bulk mode measurement. So not going to go too deep into the background on potting compounds and thermal interface materials in today's session, but for those who may not be aware, potting compounds are it's really a form of a thermal interface material that provides support to your system. It also acts as a thermal management tool. Again, really we're trying to pull that heat away from these components. And this is really important for the operation, the lifetime, the safety considerations of these systems. So whenever we're talking about thermal management, as you can imagine, thermal conductivity of these materials plays quite an important role. Now, there's a range of different potting materials out there. Again, not going to go too deep into this, but you can see some of the points on screen if this was an area of research or something that you are interested in. Again, we've done quite a bit of content on thermal interface materials, different types in the past. Definitely feel free to take a look at those. But really, I'm just going to skip ahead now to the data. So what we did in this example here is really we just compared actually MTPS to TPS measurements on these different sample types. I like this data set because one, it kind of shows some varying thermal conductivity ranges, kind of the low, kind of 1 watt per meter Kelvin up to a little bit above 2, but it also shows the type of comparison that you can get between different methods. Different options out there do have certain considerations, but in many cases you can get some very comparable data between different testing options. So kind of just looking at the MTPS data compared to the TPS here, really good agreement within about 5 to 10% across the board. And again, just an example of a kind of a basic measurement using TPS bulk mode for the data presented here. Now, kind of going into something a little more niche in topic, it's related to the temperature testing. There has been, over the years, some very, noted issues with high temperature TPS measurements. So the TPS, or hot disk style sensor, that can kind of be used interchangeably. This method is available by, many different different vendors out there. Of course, we are one. There are other groups that offer the TPS method. But if you take a look in the literature, there is really a known issue, and it's been this way for a few years now, specifically between about 300 to 500 degrees Celsius, where people will note, extreme bias in the high temperature results. Many papers will exclude the data or just simply not test in the problematic range, or they talk about corrections that need to be applied. So it's something that's been known as an issue by folks for a few years now. And this is just a data set I pulled from one of those papers referenced there. You can see the image source in the bottom, but it's really related to the sensor. So regardless of the material type, we're looking at a ceramic, a kind of polymer, metal, different type of samples here. But you see similar trends in as that temperature approaches that quote unquote problematic range in all cases. So really, again, above kind of 300 to 500 C, that error really starts to increase. So this is obviously a problem, and it's one that we've actually addressed here at C-Therm for our high temperature sensor line. So the TPS 500. This is just some example data that was collected on some reference materials, but you can see an NPL stainless steel and a standard pyroceram reported here, and just really kind of zoning in on the, again, call it the problematic range that's been observed by many groups. We are able to get really good, consistent data within the expected tolerance window across that range, and there is no post-measurement correction or additional work required. This is all just directly measured from the sensor at high temperature. So it's been something that groups have pointed out. If you are needing high temperature data, kind of in that 200, 300, 400, 500 degrees C range, really a great solution is available for you with the TPS 500. So definitely feel free to reach out if that's of interest. Now, with TPS, frankly, where many groups gravitate towards this sensor is for some of the more advanced utility options. So I kind of, during we're talking about the principles of operation, it is a little bit involved of a measurement. We do have more simplistic options available, but really related to some of these advanced options, it can be a really great fit for certain really specific sample types. So we're going to go through each one of these in some detail, starting out with the TPS slab utility. So the slab utility, this is some kind of an example setup image there, and just a little screen grab from the ISO itself. But the slab function is really designed for testing materials that are about 1 to 10 millimeters in thickness. So 1 to 10 millimeters thick is well below the requirements for the bulk mode testing. Excuse me. But because of this, there's a little bit of a difference in the setup. We actually have your samples surrounding the sensor with an insulative backing material on the top and bottom side. So this setup does provide us with a means of doing some of these analysis. Landon there might have some feedback on the mic. There we go. Alrighty. So with the setup here, one thing just to make note of is we do need to have a an insulative backing material on the top and bottom side. Now, the TPS function for slab is designed for a 1 millimeter minimum thickness, but there are a lot of groups that we've worked with that are really trying to test, samples that might be a few hundred microns thick and very, very high conductivity. So we've actually done some testing with the slab mode on some very thin metal foils. In particular, the example showing here is a aluminum foil. I believe it's about 100 or so microns thick. And the data that we collected really showing some really good comparison to the reference value. I do need to highlight specifically that due to the thickness being much lower than the standard ISO requirements, it's technically operating outside of that standard range. But sometimes, if it's in an R&D setting and you don't really have a valid way of getting results, sometimes you can make some certain adjustments here. And clearly with this sample type, really good measurements coming in even at like about 100 microns in thickness. The next utility we'll take a look at is the anisotropic utility. So, it's right in the name. It's for testing materials that are anisotropic in nature. Just wanted to kind of highlight a little bit of a data set here. With the anisotropic utility, you do need to manually input the heat capacity and density of the materials that you're working with. This is required in the software because the software is doing an analysis. It's doing some work behind the scenes. It's all the anisotropic utility is well defined in the ISO if you want to learn more about that, how it works. But ultimately, what you get from the output of your measurement is both an in-plane and a through-plane thermal conductivity. So just kind of an example set there. And again, if you're dealing with anisotropic materials, really you're going to want to use a specialized mode for that to make sure you're collecting the most accurate data as possible. And then lastly, thin films. So the thin films utility is probably one of the more popular options when it comes to the TPS. Really allows you to test really, really thin samples down as low as about 10 microns, and these being polymeric freestanding style films. So again, this is not one that we'd really recommend for extremely high conductivity materials. But if you do have thin films, whether they're for electronics, packaging, different types of applications of that nature, this is a great option to understand the thermal performance, because at 10 microns or even 50, 100 microns, testing options for that size sample can be quite limiting. Or there's things that you need to do to the sample, maybe producing a larger form factor to get a valid measurement. So with the TPS, it gives you a way of directly assessing that type of material. You can see this setup involves this iterative measurement process where you take a blank measurement, so it's your sensor around a conductive backing material, and then you successively add in the layers of the thin film, taking measurements as you go. But this is ultimately a way to test, again, really thin film materials. Here are some example conductivity results that were obtained on some kind of called it standard or known, well understood materials. So the measured results compared to literature in very good agreement there. Now, the other thing with the thin films, and recently we've seen quite a demand for this, but having the ability to test with the different size sensors as it relates to the diameter of the film that's needed. So on the Trident platform, all of our sensor sizes are available to use for thin films testing. And specifically when you get to the 6 millimeter sensor, that really allows you to test the smallest possible diameter film. So, if you're limited inherently on the size of material that you can produce, if you can get it to at least a little over 6 millimeters in diameter, then there's an option available for that testing. And then you can kind of see some reference data. So we tested the same material just with all three different sensors. The results were within a couple percent of each other and also bang on with the reference value. So this was a peak thin film material. Another aspect, and again for thin films, again it's one of the more popular options, is the ability to test at varying temperatures. So many groups, with its initial analysis, maybe room temperature is fine for what you need. Certainly, definitely quite a good fit there. But we also have the option to do testing up to at elevated temperatures. So perhaps that's related to a process you're looking to mimic or a certain condition, what have you. Again, you can kind of see here some reference data collected comparing some material performance across a temperature range. So with the TPS, again, different sensor sizes, different temperature options. These are all things that we can look at and find a solution related to your needs. So going to be wrapping up here shortly. So just kind of wanted to summarize. So our transient plane source is one of three methods, one of three transient-based techniques that are available on the Trident platform. The TPS is very versatile in the type of material it can test with respect to whether it's a bulk isotropic material, a slab, anisotropic thin film. But if it's a solid type material, TPS, really great option there. The sensor size flexibility really does provide you a kind of the ability to test a range of different sample sizes. And lastly, really the high temperature options being available kind of covers, different types of testing conditions that you need to run at. And of course, with our TPS 500, noting 0 performance gaps with our system. So kind of going into a little bit of an outro here. First of all, I'd just like to say thank you for joining here today. And also happy holidays. This is our final webinar of the year. We put on these monthly or sometimes a few every month. So I do recognize some names in attendance that might have been on a couple of these in the past. Thanks for being with us throughout 2023. And I hope your holidays are good. We will kind of just go through the standard outro with respect to if you did want to learn more or kind of go into it. We do have a range of resources available on our website, different past webinars, different tech libraries, publications, and journals. You can definitely take a look at those. Upcoming events. So it is the end of the year, but if you happen to be in Germany or in the area, we will be, or I guess with the time difference, we were at the Thermal Management Expo, booth 1004. I guess that's probably closed for the day, but this was one of our last events of the year. So just wanted to flag that. Normally, I'd have some upcoming webinars to kind of present to you, but again, this was the last one for the year. We will be updating on LinkedIn and on our website, so stay tuned. In 2024, we will be kicking off the year, I believe in the second week of January, with some initial webinar content, so be on the lookout for that. And yeah, give us a follow on LinkedIn. So whether it's keeping up with the upcoming webinars or different blog posts, this is where we'll post it first. So you can definitely keep up with the latest info there. If you were interested in maybe taking a measured next step, you wanted to book a demo, we do have the ability to do the live video consultations, take a look at different materials as they relate to your testing. Or if you need a quote, definitely feel free to do so through the links being posted. I will make note that this was a Black Friday special, but it is continuing on till end of year, and it's related to the TPS system in particular. So if you were looking at potentially getting a TPS and it's something that you wanted to move forward with before end of year, there is a sale on right now, a little 20% off, up to 10K in savings. Definitely feel free to take a look into that if it's of interest. And with that, coming in just under the half-hour mark, at this point, we will end the formal portion of our session and enter into the Q&A. So